Hello, everyone. So I'd like to welcome you to our presentation. The presentation is extending the zero trust security model for containerized applications to the public cloud. So first off, I'd like to introduce my colleague, Sharif Awad. You know, Sharif was definitely a delight to work with. He's a really smart guy, and so it was a lot of fun. We were able to bounce a lot of ideas and make a lot of progress on this presentation and the demo we'll be doing. Sharif is an SDN solution architect lead at Nokia, a part of the Nuage Networks division.
Yeah, thank you, Jason, and it's a pleasure to work with Jason as well. He's our orchestration guru. So he represents VNO, Virtual Network Orchestration for Nokia in North America. And yeah, look forward to presenting with you.
Excellent. There you go.
Thank you. OK, so in terms of the agenda for today's talk, we just want to explain. OK, apology, first of all. People told us the title was too long. So we tried to shorten it, but we weren't able to. So, you know, engineers, we would like put everything in the title. So, but the agenda is very simple. So we're just going to start with an overview. What's the landscape? What are we going to talk about? We're going to talk about how we got to this point, because really, with SDN and OpenStack, it's been a journey. It's been quite a few years, and we've made a lot of progress. I want to talk about, the evolution of this type of model. I want to talk about our vision, like where do we see the future of containers in public clouds, and how do we secure those workloads? We'll talk about the challenges to getting to that point. Then we're going to discuss a solution. Now, we implemented this solution using Nokia technology, but the reality is this is a very open solution. So you could use any open source SDN controller, uses OpenShift, uses Kubernetes, uses OVS. So it's a very open solution, and you can implement it using whatever your preferred vendor or preferred open source solution is. And then we'll have a brief demo where we'll show you what we were able to accomplish, and we'll open the floor up for questions. OK, so what are we going to talk about today? OK, so what is the zero trust model? And this term is thrown around a lot, and a lot of people still don't quite understand exactly what it is. So zero trust is this idea that assume everything is untrusted. Assume everyone is out to get you. And I know this is kind of a bit of a paranoia, right? And most people are not out to get you. But the idea is never implicitly trust anything or anyone. So always authenticate, always authorize, always encrypt. Always assume that someone could be listening in. And if you have business critical information, you want to protect that. And you're going to see that we've always made this assumption on the internet. Like when you connect any device on the internet, there's always a firewall there. There's always intrusion detection. There's malware detection. But we never assume this about public clouds. We assume that if we're running something in AWS or Google Cloud, these guys are keeping our stuff perfectly secure. Nobody's spying on our data. When I talk to Alexa, which is a cloud service, I'm assuming that nobody's listening in on my conversation, right? Which turned out to be an incorrect assumption, right? So these same people who are running all these services are running our public clouds. So we kind of have to assume that someone is listening in. That person may be listening in to help us, but maybe they might be trying to hurt us. So let's not make any assumptions. So what are we going to do? We're always going to give everything minimal access privileges to start. We're going to use microsegmentation to make sure that you can only talk to those endpoints, those services that you absolutely need to talk to. We're going to authenticate everything before it can connect. And we're also making sure that all the data path traffic, the user plane traffic, between endpoints. And those endpoints could be users, they could be applications, they could be VNFs. It doesn't matter. Whatever is sending traffic to whatever else, that traffic absolutely needs to be encrypted, regardless of the environment and the underlay that's being used. And we also need to be vigilant, right? We constantly have to monitor the communication between these endpoints and create signatures. Compare those signatures against what we expect to see, and then take some threat mitigation methods if we detect intrusions, right? And if we implement this architecture, we can be very, very confident that our applications running in public clouds are just as secure as if we ran them in our own private clouds where we control the physical environment. OK, and what has been the challenge of this zero trust model? The challenge has been islands of connectivity, right? You have this private data center. You have a third-party data center. You have a telco cloud. You have a public cloud, right? You have a branch network, right? So these are all islands of connectivity. And within these islands, yes, you have an SDN controller. You have a cloud management system, right? You have all of these tools, and you have policies in these islands to implement security. And that security is focused on the security needs of that island. But what happens when we have multi-cloud, when we need to connect all of these islands together, when we need to move applications into public cloud? How do I bring that all together? How do I make sure my policies and my authentication, my authorization, my encryption is end-to-end, right? And I manage it as one unified service. So that's really the challenge we're trying to address, right? And really, orchestration plays a very big role in that, right? Because in the end, we have so much complexity, and no end user is going to want to understand all this complexity of the multi-cloud. So you need some sort of a higher level, master of masters, if you will, that understands how these things fit together and provides a very simple set of abstractions to consume these services. And with that, I'm going to hand it over to my colleague, Jason.
Excellent.
To explain how we got to this point.
So the journey is pretty interesting. I think it tells a good story because there's lots of technology. And we've been building off of things we learned from one setup, moving it to the other, coming back to the other, and applying. So let's start with what we've been doing for a long time, and we've had a lot of really good presentations in the last few years at the OpenStack Summit about the private data center. Your SDN in the private data center. In this case, because it's our own private data center, it's secure. The whole thing's firewalled off. When we're talking about hypervisor to hypervisor, you're just sending VXLAN traffic, and there's no need to do any sort of encryption because you're in your own premise and you know that you're safe. And from this SDN technology, we grew into another technology. So that's the one on number 2. And this other technology is called SD-WAN. So SD-WAN is actually a very, very interesting concept. The idea is we already have all these existing networks in place, like the internet. The copper is there. So, let's say I have a location in Ottawa, I have a location in Denver, and I have a location in New York. So I'm going to ship a box to each one of those locations. The boxes are going to connect to the internet, and they will bootstrap into this private VPN service. So this is a virtual VPN service, so it's completely software-based. And because it's fully software-based, you now have the ability to create all these complex policies and rules and do all these fun things because you can program it. Essentially, you're creating this private VPN service over top of the internet. Now, when we're talking about SD-WAN, there's a learning curve, right? In SD-WAN, we're not in our own private data center, meaning security is quite important. So, the first one main difference is we're doing VXLAN over IPsec. And that way we can ensure from branch to branch our data secure. And this technology itself today is used all over the place. Think of banks. Banks are using this to communicate branch to branch. So it is extremely secure. Or you think of a shop, like I saw the other day, Lululemon posted a job posting for an SD-WAN engineer. They wanted to essentially connect all their locations together. Each one of their locations is a branch. So in this case, Lululemon wanted to connect all their stores together or maybe connect it back to some back-end application. So from this SD-WAN service, we've been able to gain a lot of information about how to securely send data from one point of the world to another using this SDN technology. And that's important for our journey because it's now going to be about how do we extend that information back to the public cloud, build off what we've learned. So the continuation of the journey has been, connecting, right? So on the left side of my screen, I show an SD-WAN service. On the right-hand side of the screen, I'm showing a data center, whether it's a virtual private data center or maybe it's a public cloud. But the idea is SD-WAN on day one started as point-to-point connectivity. And SD-WAN, if we talk about today, it has grown. It's talking about branch-to-branch connectivity, but also interconnecting traffic into a private data center where you may host a value-added service or an application like a firewall, or you may host some form of application in the public cloud. So the definition of SD-WAN has really grown from just point-to-point connectivity over an underlay to SD-WAN to private cloud to public cloud. And when we've been doing this, over the SD-WAN side, we've been doing VXLAN over IPsec. And then we've been assuming that once we get into the data center, whether it's our own private premises or public, that it's safe. So essentially, we'll be going and taking this VXLAN traffic over IPsec. We'll go through some border router and convert it to unencrypted traffic, and then send it to our end VTEP. So on the right side of the screen, it's unencrypted. On the left side, it's encrypted. Now, if this isn't your own private data center and you're a bank, you may be a little bit concerned about that data that you're responsible for. But today, what we've been seeing, in the industry is once we get into the private data center, we've assumed the data is safe. So this next slide's about the unified multi-cloud solution. My colleague Sharif talked about these islands of connectivity, right? And the idea is we want to move to a unified, we talk about the single pane of glass approach, where we have a centralized policy, centralized network controllers, and then we move the data plane, whether it's in, whether it's an OpenStack, whether they're branches, whether, it's an OpenShift setup in the public cloud. These are all just data path endpoints connected to some form of centralized policy and control. So the next conversation is about why orchestration. Now, when we've expanded into this multi-cloud, we had the word single pane of glass. We've exposed a lot of technology. We've exposed a lot of capabilities to the end user. On the left-hand side, I'm showing SD-WAN, and when we deploy an SD-WAN service, there's a lot of dynamics to it. We have different type of underlays we need to support. We have different types of branches we want to support. We have scenarios where we may want to host a VNF on a branch like a firewall, some decentralized VNF. In the data center, let's say it's a private data center, there's going to be a whole scale, let's say private application, a whole scale of value-added applications we may want to host. And then there's a whole scale of various third-party clouds that we could expose. And orchestration's role is to essentially make this technology easily consumable and provide some form of abstraction to the end user so that it can be easily consumed. So whenever I talk about orchestration, there's usually three things I talk about. The first thing is the single-click deployment, and that's what most people think of orchestration. On day one, I'm going to orchestrate some service. That service is composed of these objects, and they're related in this way. And we're going to be able to orchestrate it 100 times, and it orchestrates the same way. The next two objects are day two, and I think they're just as important as the single-click deployment. So when we talk about service updates, this is a revenue generator for service providers. Continuous revenue. So let's say on day one you start with point-to-point connectivity. I now need to understand what that service is composed of and expand it into a data center. So orchestration will need to understand all these different objects here and how they're related, and how can I chain traffic into a data center, deploy, let's say, a private firewall, and send traffic out to the internet. The next aspect is maintainable service. How do I maintain that service while the resources below us may change? On day one, you may have a product offering. On day two, you have a new product offering. How am I going to migrate one of my customers on day one to day two? How am I going to handle the scenario that when my SDN controller below us upgrades? How am I going to handle the scenarios that the product offerings, the VNF offerings have changed? How do I adapt to those situations?
Okay. Thank you so much, Jason. So what's the challenges to achieve this vision? So we talked about the idea of these islands of connectivity. We talked about different policies applied. We talked about the benefits of orchestration. And now let's identify exactly the problem we're trying to solve here. Okay? So we want to make sure in the public cloud that we can authenticate our nodes, right? So anytime say we're running Kubernetes or OpenShift, anytime a host comes up, it has to be authenticated because we cannot trust it implicitly. We want to make sure that we secure traffic between applications in the public cloud, so between pods, and also between users in the branch or applications in our private data center and between the container applications. And we want to provide, obviously, visibility. So we want to make sure we can see everything, we can monitor it, we can understand the traffic flows, and we can identify potential security weaknesses. And we want to answer this question, really. Is my public cloud reliable for security? We said the answer is no. And how can I take matters into my own hands and be the master of my own fate? Okay, so how do we put it all together? So this is the overall solution. So we have OVS-based CPE devices that are sitting in the branch. And these guys are going to bootstrap. So they're going to talk to some sort of a proxy, SSL proxy. And they're going to say, look, I'm coming up. I'm part of this organization. Here's my certificates. And I want to join this multi-cloud, the secure multi-cloud. So the proxy will then send the request up to the policy engine. The policy engine, which is running a certificate authority, will say, yes, you're approved. We generate client certificates for that branch. The branch then will authorize itself. So it'll talk to the controller and say, look, I'm coming up. I'm joining your multi-cloud service for, say, Nokia organization. Give me all the policy. So then OpenFlow is used from the controller to the OVS instance to download a set of rules. That rules will say, how do I connect to all the other endpoints? What are my symmetric traffic encryption keys for the data path? What are all my rules, distributed virtual firewall rules? What other branches can I talk to? What applications can I access? What applications can I access in my public cloud? And so on. Even stuff like my QoS policy, quality of service, DPI, all that stuff is programmed through policy from a central controller based on service constructs at the orchestration level, right? So now this branch is onboarded. How does it talk to a container running in the public cloud? So what we do in the public cloud is we install OpenShift master node, and we authenticate that. We install OpenShift worker nodes, which run Kubernetes pods, right? And then what happens is we bring up an application within a namespace within Kubernetes. And as soon as that application comes up, we have an SDN agent running here that will talk to our policy engine and say, we have a new application coming up. It needs to be able to have connectivity into this multi-cloud. So again, the same type of authentication, authorization is done. The SDN agent will actually be provided with symmetrical traffic encryption keys, as well as network policy. And now it can do end-to-end VXLAN over IPsec. So this branch can do VXLAN over IPsec, over the internet, over private MPLS, right into the public cloud, and terminate that tunnel right on the worker node, right? So right on that OpenShift worker node. And then that OpenShift worker node will then route that traffic to the container, to the pod, and eventually, if exposed via service, to the container within that pod, right? And so now I have connectivity between branches, secured. I have connectivity from branch to that application. But what happens if this application is a web front end and needs to talk to a database front end that's hosted in the public cloud, right? I want to make sure that this traffic is also secured, right? So I can use my SDN controller to actually set up a rule that says that these two applications are part of different policy groups. And then between these two policy groups, I'm going to allow only a certain port, which is my database port. And then this database server can reply on a certain port. And I can also make sure that this traffic is encrypted. So this is VXLAN over IPsec. And so I have full control. Not only is my traffic encrypted, these guys are authenticated, but even the service traffic that they send between them is restricted based on centralized policy. So if this database server gets compromised and he's trying to hack into this web server because of the microsegmentation, because of our analytics, because of our granular zero trust policy, he's basically going to be isolated. He will not be able, even though he's authorized, he will not be able to attack or to bring down my multi-cloud. Right? So this is the vision we're we're trying to achieve. And this is what we'll be demoing for you today. Okay, so I'll hand it over to my colleague Jason to talk about our demo.
Awesome. So yeah, so Sharif kind of just showed how we've extended the idea of using VXLAN over IPsec all the way from the branch to the pod, and then we would only decrypt the traffic once we've reached that point. So we decided to do a demo and present that to you guys. Part of, for myself, this will always be the OpenStack conference. So one thing we thought would be fun was let's build this on top of an OpenStack infrastructure. So we built a lab. Actually, we used hardware that was available to us out in Poland, and we put together an OpenStack lab there. And on top of that, we were able to demonstrate the solution that Sharif just presented. And it's quite an interesting solution, as we've taken the concept of SD-WAN and how we've been dealing with those endpoint VTEPs and applied it to these public cloud. In this case, it's an OpenShift setup, and we've applied essentially those concepts from SD-WAN into that OpenShift CNI. So the lab topology. So in our case, we have a management network and a data network, so a data plane. So this is a layer 3 network, various subnets between the different components. So on the left side, we have our orchestration engine, VNO. We have the VSD, which is the policy engine of Nuage. We have two SDN controllers. The first one is for the WAN, SD-WAN side. The other one is for managing the public cloud side. We have the proxy. And then on the right side, we have our OpenShift cluster composing the master and nodes powered by Nuage SDN. So let me bring up the demo video. Perfect. So let me just click that. Oh, for some reason it doesn't show. It's not showing on the screen. Do I need to? I think it's because you take over.
It's still not showing yet. Do you know why it's not showing on the screen? I don't think. Let me check 1 sec. Yeah, we don't trust the projector, so. Okay.
Oh, we're doing unplugged.
1 sec. Let me just check here. I think I'm still plugged. Oh, here it is. I'm on. Let me do duplicate.
Yeah, perfect. That works.
It's gonna work. Yeah.
Perfect.
Okay, excellent.
Awesome. All right. So the first thing we're going to show you is the orchestration of the branch into this service. And then Sharif is going to show you the actual underlay, showing the encryption of packets from point to point, from branch to pod, or from pod to pod. So let me start this video. It should start. Perfect. So I'm a bit of a wild person with the cursor, so it's going to be all over the place. But so it just starts off in our dashboard where we have one SDN controller connected, and that's our Nuage platform. From there, we're going to go into the catalog. In the catalog is where we store our network service descriptors. These are files that define what the service is composed of. It's almost like you can think of a blueprint of the service. So this is the word that you'll often hear is model-driven orchestration. So we're going to select this OpenStack Summit branch. From here, we're going to get a list of inputs that we can enter. So the first aspect is just the name of the service. So this is the Ottawa branch. The enterprise is associated to an enterprise concept in Nuage. We have essentially the branch name that we want to create. Where is this branch located? What hardware is being used? What bandwidth plan the subscriber has subscribed to? Which VSC pairs are we using? So controllers. We have the ability to connect to the internet in different ways. In this case, we're just going to do DHCP, so dynamic, so we don't have to put in any IP address information. We're going to enable local breakout, so that gives also the option from the NSG or the branch. You can break out to the internet or go into the private VPN service. OpenShift is the name of our namespace in our OpenShift setup. And then the last package is our LAN service information on the NSG. So we're going to create that. And once we create it, we now have the opportunity to deploy it towards the SDN, and that's when the actual service will be instantiated. So we're going to select, in this case, we just have the new Azure SDN in place. Click deploy. So we're going to let it deploy the service. So from here, it takes us to a network service instances page. So this is all the network services we've deployed. So I cleaned the setup so it's clear what's going on. So we're going to click on the network service to find out what jobs are being run. From there, we're going to go to the event log. And in the event log, we have our deploy running. So we're just going to click on the job ID to see more information. So we did a create the input variables. And then we click deploy, which actually instantiates the service into the SDN. So from here, we've already started, and we've created a whole bunch of different objects. So as we mentioned with orchestration, it's not just about provisioning objects. It's about creating a large set of related objects. So when we talk about new Azure and we need to define a LAN service, we need to create a domain zone subnet, which are all interrelated, and then that domain node subnet needs to be associated to some vPort. That vPort will then need to be associated and bridged to, let's say, an NSG LAN port. So there's a relationship to understand, and those relationships are very important when we talk about updates. That's how the orchestrator knows what it needs to touch so that it can update the service without affecting the end customer experience. So we've deployed our service, and I'm actually going to pause the video shortly, but I just wanted to show quickly kind of what that relationship looks like. So we use an open source tool called Cloudflow to display Mistral workflows, which is the workflow language that we're using underneath the hood. From there, you're going to essentially get a diagram showing the sequence of events that it's gone through to deploy the end service. So there's quite a bit going on here. So you'll see essentially quite a bit of objects being deployed. So let me just move on to the next video actually now so that Sharif can show the data path encryption that was happening.
Sure.
I'll let you change that.
Okay, let's go here. I have it open actually already. Yeah, this one here. Perfect. Okay. Thank you very much, Jason. So what we're showing here, this is our GUI for our SDN policy engine. So basically we're showing they have, after the orchestrator went through, the branch is bootstrapped, it's provisioned, the WAN and LAN connectivity at that branch is created, and the overlay network has been created, and the branch has been connected to that overlay network. You notice that it's green, means it's connected to the controller, and it's been authorized. So he's now officially joined the multi-cloud. In terms of the actual service, so that'll be under networks, we have an organization called OpenShift, because we're connecting this branch user into the public cloud. And that's based on a template. What happens is we create these different zones, which correspond to OpenShift or Kubernetes namespaces, right? And then we have policies that control how traffic can flow between these zones. These are kinds of policy enforcement points, and this is how you do multi-tenancy or segmentation within an organization, right? So it's one enterprise, but we're segmenting into different policy zones, which within each policy zone, we have a subnet. So this is automatically allocated from a pool. And just want to quickly show you that our nodes within OpenShift, which we call them data center gateways, have been also bootstrapped. So again, we don't trust them implicitly. We've bootstrapped them. You see that they're getting a certificate as well. And green means they're also authorized to connect to the multi-crowd. And you notice that we have encryption enabled on each of those. So any traffic flowing between these OpenShift nodes will automatically be encrypted. So let's go back now to the service layer. So all our endpoints have been bootstrapped. And let's see how we create a service. So we created a Nokia organization, which creates a Kubernetes namespace, which creates a zone. And then we've created 2 subnets. One subnet, which will be our container application. So we're using BusyBox here. And we've basically brought up 2 different containers running on different nodes, representing applications in the public cloud. And then we also have a host that's connected behind the branch. And that will represent a user at a branch that's accessing an application within the public cloud. So you see it's different subnets. So we can create policy. We can have policy between branch to public cloud. These are also policy enforcement points. I can say that this user at this branch can access this application, not allowed to access this application. I can control the traffic flow between applications. It's all policy-based, and it's all hierarchical. So it's very easy to apply policy at different levels and have policy at more specific levels override policy at the higher level. So you can really, the sky's the limit with respect to the amount of security that you can implement. It's all visual, and it's all API-driven as well. So it all can be orchestrated. Let's just move a bit forward in the video. So I know it's going a bit slow here. Okay. Yeah, so now let's go to the good stuff. So I'm on my Kubernetes master here, and I can see all my pods that are running, right? So these are my nodes, are all ready. I have the 2 BusyBox pods running on different hosts, if you will, or Kubernetes worker nodes. So I'm going to log in. Well, first of all, I'm going to log into each of those containerized applications and validate that they're connected to the OpenShift network, and they all have automatically gotten IPs from the SDN solution. So let's log in first to the first container application using RSH, remote shell. Okay, so now I'm actually inside the container right now. And if I do IP address show, I see that within that subnet that we showed before in the SDN layer, I have actually got in dynamically an IP address, right? And now if I go into my other container application running on the second node, and I do IP, I have an address, but in a different subnet. So that allows me to do vary policy between these subnets. Sorry, it's the same subnet, but different address. My apologies. So let me ping now between both of these containers, just to verify that I have IP connectivity. So you see my ping is successful, right? So I'm going to leave the ping running. Okay, so let's start the ping and leave it running. Okay, so the ping is running. I'm going to go on my other container application. I'm going to ping back to my other application. So let's think of these as one of these as a, sorry, I'm not pinging back, sorry. I'm actually checking on my node itself. So I'm on the worker node. And you can see the traffic is encrypted using IPsec. So it's VXLAN over IPsec. And we're using ESP. So this is completely secure traffic. And the VXLAN tunnel endpoints are actually the worker node underlay IP addresses. So I've verified that BusyBox 1 is sending encrypted traffic. And I've verified that encrypted traffic is being received at BusyBox 2 that's replying back. So it's bidirectional encryption between my container applications in the private cloud. So that's working. So now let me go on my branch and verify that I can reach applications within the public cloud. So I'm gonna make, this is representing a user at a branch. He's sitting on a workstation. So let's check, first of all, that this user has gotten an IP address in the virtual overlay network. So this is the NIC that's connected into the branch gateway, the OVS gateway. So he's gotten an IP address dynamically. And he's connected into the OpenShift network. And now I'm going to ping the containerized application running in the public cloud. And I validate that that's working. So I have bidirectional connectivity from my branch into a container running on the public cloud. Okay. I'm logging now into the gateway itself. So this is the OVS gateway. And I'm verifying that ping session that's running from my user behind the gateway is fully encrypted. So you see the endpoints of that session. The dot 10 is the gateway underlay IP, and the dot 2 is the Kubernetes worker node running in the public cloud. And I have full bidirectional end-to-end encryption of all my traffic, right from the branch into my container in the private cloud. So right now I'm safe, whether it's branch to application, application to application, application to branch. It's all policy-based, it's all SDN-based, it's all orchestrated, and it's all secured, right? And we think that this is the model in the future, right? Like, because what we're seeing here is everything is moving, well, not everything, but a lot of things are moving to public cloud. And what's preventing people from moving, banking or stock exchange or even telco applications is really the PCI compliance and the security. So if you can solve this by end-to-end encryption authentication, and if you can use public cloud resources but maintain full control of the SDN and full control of the end-to-end service, then I think it's going to become a lot more appealing for a lot of people to embrace the public cloud. So we're very happy the demo worked. Of course, we recorded it, so we mitigated that failure opportunity. But so we have a few minutes left, so we're more than open for questions if anyone would like.
And
okay,
perfect.
Hello, this is Omar. Thank you very much for this presentation. It's really nice. I mean, that's the biggest problem with the banking industry, actually, like you said. What do you think about encrypting the data on the disk as well, on the servers, not only through the communication, but also on the disk as well?
Not a bad idea.
Can we apply this to the same technology, or?
Well, so in this case, we've built our cloud platform on top of whether service offerings there. Yeah. So you have that capability to do that. Now, you have to make the decision about what type of data you're storing. Is it worth it? If you're a bank, for sure it's worth it. If you are, just Joe Blow doing your own small thing, maybe you're not as concerned about the data you're storing.
Yeah. But that's actually a very good point. And we're partially there for what you said, because all of our corporate laptops have disk encryption, and that's not optional anymore. That's mandatory by the active domain policy over the organization. We actually can't connect to the organization unless it validates that our disk is encrypted. We can't connect to the domain. But your point about applying that same principle for disks in the public cloud, I think that makes perfect sense. So as you authenticate people to connect to the domain, you want to make sure those endpoints are secure. They have the latest patch updates. They're running the supported version. So it's not just a matter of presenting a certificate. It's also presenting proof that I am secure enough in terms of disk inscription, in terms of firewalling, all the other good stuff. No version, old versions of SSL, or all those issues. That is a great idea. And if we present again, we'll include it.
We'll do that. We'll update our OpenShift setup.
So while this is great, it seems a little early to call it zero trust because, let's say I'm a bad bank, I would point out that there's no secure processors, there's no HSP, so my data is not protected from my cloud provider capturing my symmetric key material, capturing my traffic, and later decoding it for a government subpoena or whatever. Is that fair?
I'd say it's true and false, because I think we can't, with OpenShift, we should be able to add some form of storage that we build on top that we can encrypt. I do think there is probably lessons to be learned and further security to be put in place in OpenShift to be able to meet some of those requirements you mentioned. But so I wouldn't say we're fully there, but I think we're getting to the point.
Yeah.
Oh, thanks.
No, that's actually, just to add to what Jason said, that's actually a very good point. So what we do on the SD-WAN side, and I think we were all talking about how we take the SD-WAN security and we apply it to public cloud, right? So we actually have, and I'm terrible for naming things, so we have a secure element that runs on our gateways, our CPE gateways, that is encrypted and that stores the private keys. And that's a hardware secure element. And if that's tampered with, we disable access. So you cannot, if you take one of our SDN gateways and you try to tamper with that secure element, and all of our operating system and stuff goes through that secure element, right? So I think what you're saying is that you would need some sort of, what's that called, that secure element? I mean, TPM, right? Yeah, TPM. So the TPM element. So it's almost like what you're saying is that the public cloud would have to expose some sort of a TPM that only the user of that cloud would have access to. So almost like a bare metal service where we would be assured that the CPU cores that were assigned cannot be capturing a copy of the data or capturing your keys, right? Because really the keys are the critical point. If you have those, the PKI keys, I mean, everything, all bets are off at that point. So you're right that our solution protects you against other banks that are hosting their applications in public cloud or some security problem in the public cloud, but not against the hardware administrator of that public cloud. So there's still the gap there, and we'll have to think of how we solve that problem. Right? That's a very, very good point. Thank you. Okay, cool. So, please.
Can you go to the slide? Well, I guess maybe it was the video, but essentially my question is about scale, right? So
okay, sure.
In your demo, you only had one or two VNFs or one or two nodes. How would it scale to thousands of VNFs or something like that? And then you mentioned there's APIs to essentially orchestrate it, but do you have any slides talking about the APIs? Or?
Okay. So maybe I'll take the scale question, and Jason can take the API question. So scale has been a big challenge in SD-WAN, for sure. We have now big service providers, enterprises that say we have thousands, even hundreds of thousands of branches. And doing full mesh with a full mesh of VXLAN over IPsec tunnel with the key distribution, with the encryption, is very difficult. So what we've leveraged at the branch to achieve that type of scale is a few things. So at the data path side, we're now embracing technologies such as SRIOV, DPDK, so pinning cores and assigning that, and that actually has worked quite well. And now even the public cloud providers allow you to run those data path acceleration technologies. Obviously, you pay more for them, but they are becoming available now in public cloud. So that will help us in data path. What helps in data path as well is policy. We don't allow by default full mesh. We do hub and spoke topologies. Because reality, most of the communication is branch to cloud. It's not branch to branch, except for VoIP and other stuff. So there's cool tricks you can do to limit the problem of the full mesh, right? That's from a data path. Now, from a control plane point of view, we have something called federation. So we actually deploy multiple SDN controllers. So for example, if you had a country like Canada, we might deploy an SDN controller in each province. And then we federate them using multi-protocol BGP with the EVPN address family. So each controller only manages a limited set of endpoints, but they have the full picture of the network through this federation. And this is the technology that powers the internet. So internet, we know about, route reflection on the internet. So the fact that you can have this hierarchical route reflectors and you can scale out, because the internet now has almost, I think, 500,000 routes and so on. So we use those techniques in the control plane. We're still challenged at the management plane because of the bottleneck of the API service. So the question is, we're looking at a technique for federation, so creating multiple API endpoints that are federated, and then having almost like a manager of managers to take the API request and farms it out. But maybe Jason can speak a bit.
Yeah, so from just nod, I guess, or answer. From the API perspective, you're more interested in the actual APIs, how we compose the service, or are you talking about from a performance aspect on the control side? Okay, so I'll answer. All right, so we didn't show anything with the APIs. So what we do within our orchestration engine is we have a plugin, and that plugin exposes Tosca types in our templating. Now, the plugin has the understanding for each Tosca type. What do I need to do when I create the object? What I need to do when I terminate the object, right? What do I need to do when I update the object? And those all associated with APIs and Nuage. Now, this is where the fun part happens. Nuage actually exposes its APIs publicly. So, they have a true REST API, which is very nice and very important. And it's publicly available just on GitLab, and you can anyone get it. It's actually the one we use from VNO. And because it's the true REST API, we're actually able to auto-generate our plugins. So we actually keep the OSS layers agnostic from the Nuage version below us, because when we change Nuage versions, we just auto-generate a plugin, and we can do that because it's a true REST API call. And we keep the OSS blind to that. So our templates are independent from the plugin in the sense that the template will stay the same. The modeling in the plugin will update, and we can continue using that template to deploy the same service on a newer version of Nuage. So it's a good question on the API call. So API, when it comes to orchestration, definitely want a REST API. if it's not a true REST API, you often run into problems because then you got to start hard coding your plugin development. The other aspect is from a performance base. We're able to control, performance-wise, we're able to control the performance through orchestration, through our templates. We create a lot of relationships, so when we do see performance problems, we are able to often mitigate it through our template engine, through relationships. So we can often, instead of doing a whole bunch of things in parallel, we'll then put maybe sequential tasks, or we'll actually change the way we do the API provisioning through special Tosca objects, which we've done. So we've spent actually, because Tosca is a very, in many cases, a lot of people found with orchestration that Tosca sometimes handcuffed them. We've actually went out of our way to create a lot of special Tosca types that allow us to be dynamic. Because when it came to SD-WAN was really the holy grail of orchestration. And when it came from moving the data center to SD-WAN, a lot of orchestrators in the market had trouble. In many cases, because they were legacy service fulfillment services, just kind of slapped on the word cloud orchestration, and they weren't able to actually handle SD-WAN. So SD-WAN's fun because it's very dynamic. So if you create a very strong Tosca engine and a strong templating system and a strong way of creating relationships, then you have a lot of power at your hands.
Okay. Anyone else would? Okay, so I'd like to thank Jason and thank all of you. Thank you so much. It was a pleasure to have you with us, and hope to see you soon.
And thank you, Sharif, as well. Fine job.